Virtual Precalculus, Section 13.3, Probability, and Introduction. So we're moving into probability, where we supposedly have some knowledge of the entire population, and we use that to predict something about a sample taken from the population. And there's just some vocabulary really we need to look at the beginning. An experiment is something in which you test a random variable, like flipping a coin, and maybe we'll flip the coin 4 times. The sample space for this experiment are all the possible outcomes, in this case H or T. Sometimes your book uses these squiggly brackets with items separated by commas to represent a list of things separated by or, heads or tails. So suppose I have a trial and I get heads. A trial means I flip the coin, and then I have another trial and I get tails, and a third and a fourth trial where I also get tails. So several trials make up an experiment. The theoretical probability for a fair coin to get heads would be 0.5, 50%, and to get tails also 50%. In this experiment, we found an experimental probability that we got heads 25% of the time and tails 75% of the time. Important facts about probability. A probability has always got to be between 0 and 1, that is between 0% and 100%. Because 0 means that it won't happen, and 1 means that it will. And everything in between is varying degrees of likelihood. But you can't be any more certain that it will happen than 100%, and any less certain than 0. Also, the probabilities of all possible outcomes have to always add up to 1, because something has to happen. In both the theoretical and experimental lists there, you can see that the probabilities do indeed add up to 1 or 100%. So those are important things to keep in mind, no matter how complicated it gets. Okay, I find this example to be really helpful in understanding a whole range of different little ins and outs of probability, so we're going to spend quite a bit of time on it here. I'm going to flip a coin, and the sample space for that is heads or tails, and then I'm going to roll a die, a number cube, you know, the kind of things they have in casinos with a 1 through 6 on it. And so the sample space is 1, 2, 3, 4, 5, 6. Alright, so I've just made a list of all the possible outcomes here. You can count them, there's 12 of them. And there's an easy way to count something like this. We've sort of seen this reasoning in MathSmate before. This is what you call a compound event, made up of 2 simple events, the flip of the coin and the roll of the die. And the number of ways that a compound event can occur is always going to be equal to the number of ways that each individual thing can occur within the compound event, all multiplied together. So in this case, the 2 ways that the coin can land times the 6 ways that the die can end up, 2 times 6, 12. Alright, so that's actually really important. It's called the fundamental counting principle, and it will come up again later. Okay, so we're going to try to calculate a whole bunch of probabilities here, and they're not hard, but if we look at them carefully, they will illustrate a lot of different points. First of all, the probability that we get heads. Okay, well, there are 6 ways that we can do that, and there's 12 possible outcomes, so 6 over 12, or 50%. The probability that we can get a 1 or a 5. Again, this represents or, this notation. Sometimes the word or will be written, and sometimes there'll just be a comma. And there are 4 ways that we can get a 1 or a 5. Out of 12 total, we get 33%. The probability that we'll get a 4 and an H. Well, there's only 1 way that we can do that out of the 12 possible outcomes. What about a 4 or an H? Well, I count 7 different ways to get that out of the 12 total. And what about the probability of not getting a 6? Well, that's 10 out of 12. Okay, so you may have to flash back to this to count for yourselves, but we're going to go through each of these in a little bit more detail now. The first example is really simple, and it just illustrates the fundamental principle of the way I think about probability, and that is, as you've heard me say before, happy over total. The chances of getting a head is the number of outcomes that include a head, and there are 6 of them, divided by the total number of outcomes that there are, and there are 12. Happy over total, 6 over 12. Well, that's easy. The second example is really interesting. It's an OR, and I want you to remember that in probability, an OR usually has to do with adding probabilities, and it usually tends to make the overall probability bigger. The probability of 1 or 3 is the probability of 1 plus the probability of 3. And if you look at those, when we're adding a number between 0 and 1, which all probabilities are, to another number like that, those kind of numbers are always going to get bigger in those situations. This only works for an OR which is mutually exclusive. And what that means is that the two events, 1, 3, cannot both happen at the same time. Okay, it's not possible to get a 1 and a 3 in the same trial. Soon we're going to see an example that is not mutually exclusive, and you're going to hopefully be able to contrast it with this one. But the important thing here is that because the events 1 and 3 are mutually exclusive, we can just add the probabilities to find the probability of 1 or 3. The next one is an AND, the probability of 4 and H. I want you to remember that AND in probability tends to look like multiply, and it tends to make the overall probability smaller. After all, if you multiply two numbers between 0 and 1, you're going to get a smaller number. We'll see that in just a second. Okay, so the probability of 4 and H is the probability of 4 times the probability of H. 2 ways to get a 4 and 6 ways to get an H. So 2 twelfths times 6 twelfths, 12 over 144, which is 1/12. You can see that indeed the probability of getting both is smaller than each of the individual probabilities. And that makes sense. If we need both, if it's an AND, we're being really picky, and it should be very unlikely that we will be satisfied in both of our requests. There's another caveat here. This technique only works, as we've shown it, for independent events. That is, 4 and H have nothing to do with each other in the sense that the chances of me getting a 4 don't really affect the chances of me getting an H. The coin and the die are not connected in any sort of cause and effect way. If there was some sort of magnet or string connecting the two so that, I don't know, when I got a head, then it was almost impossible to get an odd number or something weird like that, then I would definitely say that the events were not independent. But as it is, I could do the coin and the die in different rooms, and they have nothing to do with each other, so they're independent events. And to find the probability of both occurring, we can just multiply the probabilities of each individual event. Alright, the next example was to find the chances of getting 4 or H. This was complicated. OR, as we remember, has to do with addition. So this almost looks like the same as the last OR that we did. The probability of 4 or H is the probability of 4 plus the probability of H minus, and this is the weird part, the probability of 4 and H. The problem here, the reason this is a different kind of OR, is that 4 and H are inclusive events. It is possible to get both a 4 and an H. Look at this table on the left. All the possibilities, all the ways that you can get H are boxed in green, and all the ways you can get 4 are boxed in blue. Look, if we just counted them up, 6 plus 2, we'd get 8. But look what we're doing. We're overcounting this one. We're counting this one twice. And so we have to subtract that away so that we don't double count. And that's really what that's all about. So for inclusive events, if you're doing an OR, you have to remember to subtract away the AND. Weird. But it matches our earlier estimate of 7 out of 12. And the last one, the probability of not 6. Okay, this is a perfect chance to use what's called complementary probability. The probability of not getting a 6 has to be 100% minus the probability of getting a 6. And that's 2 out of 12, so 100%, or 1, or 12 twelfths, minus 2 twelfths gives us 10 twelfths. I call this the big potato. Okay? Either I get a 6 or I don't get a 6. That's the whole potato. There's nothing else possible, right? What else can happen? I mean, either I get a 6 or I don't. Another example, either I return to Tana this week or I don't. And the probabilities of those two things have to add to 100%. This trick ends up being really useful, especially in things like the birthday problem, which we'll get to later on. Alright, stay part 2.